And we're recording. Happy whatever day it is. Good
It's Friday.
Friday. I don't know. I guess I've been having too much fun making videos for college algebra and ABC. Welcome back. It's Corey and Jana, or Mr. Bobby and Miss
Hey,
Young.
we matched and we didn't mean to.
Oh yeah, it's green. But on Fridays we can wear whatever we want. Okay. So today we're going to be talking about increasing, decreasing, and constant functions. So I thought we would just jump right on in and try to get this defined. And it really means in math the same thing it means in the world. If you're experiencing an increase in temperature, the temperature is going up. So when we say that for a graph, we mean that the graph is going up from left to right. So the graph would be like that, or something other like that, okay? And it has to be from left to right. When we're talking about decreasing, you want it to guess. Oh, I was going to just draw a separate one.
I feel like we should also talk about the fact that this is increasing.
Yeah.
I think that's a little confusing because, you got this. That's obviously increasing.
Yeah.
This is increasing too, though. So just, be aware of that.
Right. And so, like, it could be like this, or it could be like this and still be decreasing as well. Okay. And we'll talk, actually, that has to do with something else that you might learn down the line if you take calculus called concavity, but we're not going to mention that here. And constant is when something stays the same. Now, this one, like, really kind of bummed me out or freaked me out. I was expecting more out of this. But what does it look like graphically is it just stays the same and it's horizontal. So a constant graph would look like this. Now, we're going to look at some examples. But we do want to see that the graph can be bent or straight and go up, and bent or straight and go down. But when it's constant, it can't do anything but just be, it's like when the person dies in the movie. Okay? So moving on. Let me get my mouse back. And so here's a couple examples of graphs. And when we talk about increasing and decreasing, we want to talk about intervals where the graph is increasing and intervals where the graph is decreasing. And we need to be careful about when I say intervals, what I mean. I mean intervals along the x-axis. Okay, so we think about it, we need to think about the x-axis and see where, that's why I put these points on this graph. There's this point here at 3, 5. And something interesting is happening at that graph here at the number 3. Now that pink line, wow, that's a pretty straight line. How about me drawing a pretty straight pink line? All right, anyway, that's happening at 3. I'm pretty proud of myself. Okay.
You should be. I'm going to jump back a slide for just a second and thought, because if you'll remember, every single one of those definitions, and they're very informal definitions,
they were,
that he just showed you, ended with the words from left to right. And that's sort of a key quality in that when we're reading the graphs from left to right, we're reading them across the x-axis. I, in fact, like to just like take a highlighter and follow along the x-axis until the graph stops doing whatever it was doing and changes, right? Okay. So the graph is, you can't see it, but it's going up, 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 up. Then it stops.
And then it starts come down.
And then it starts going down, 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 down. And I should have changed colors.
Oh my gosh. And I just want to let you know, Miss Young just finished multiple days of reading training for her new job. So thinking like a reading teacher, left to right, but you read the graph like you read word, or at least like we read words in the English language.
Right.
So those purple numbers that she highlighted, what X values has she highlighted? And that graph is going up. So we would say that to the left of 3, it's increasing. But we want to put that in, we want to talk about that in terms of numbers. So it could be, I could say 2, I could say 1, I could say 0, I could say negative pi, I could say negative square root of 2. I get real tired of that eventually, or at least Miss Young would get real tired. I'd have a great time doing it, but she'd probably be sick of me after doing, she's already sick of me doing it. So what you would say is, and I'm just, is it okay if I say increasing by like just doing the first 3? Okay. Now I could say,
too lazy to write that whole word.
Yeah, it takes forever. And you all know what I mean. It's increasing everything less than less than 3. So what we say is we can write that as x less than 3, but I'm going to introduce you to something called interval notation. So at 3, it changes. And for it to keep going to the left forever, that means forever is infinity, and that would be negative infinity because it's going to the left. Now, why did I put a bracket there? Now, hopefully, maybe you've never seen interval notation before. Interval notation, when there's a parenthesis on it, it doesn't include the endpoint, okay? So when I get to that peak at x equals 3, it's neither decreasing nor increasing, okay?
Which is such a weird thing to say. Okay. How can it just be not increasing and not decreasing?
Because it's constant. Okay, and for an instant. Now that's something that you'll take into account in calculus. But in the interval notation, you go minimum to maximum on an interval. It's a way of talking about all those numbers in one shorthand notation. Okay, and
so
then
it's saying the smallest number highlighted on that purple line is negative infinity because there isn't a smallest one because it goes left forever. And the largest number highlighted on that purple line is 3, but not including 3, so we put 3 parentheses.
And when I'm talking about where the function is falling, it's falling on to the right of 3 for numbers bigger than 3, or from 3, 4, 5, 6, 7, and there's already 6. So instead of saying that, how high can I count? I can count to infinity. And again, parentheses around infinity. We always have infinity. You're never going to get to infinity. Buzz Lightyear was an idiot. All right. He was stupid. Okay.
Bobby, there are different sizes of infinity. You can go to.
You can't go beyond infinity. You can't even get there. Okay. Buzz is an idiot.
There's an infinite number of even numbers, and there's a larger infinite number of whole numbers. I mean, of integers. So I'm just saying.
Take a second and tell me where this graph increases, the one in the middle, and where it decreases. You can pause the video and write down your answer. Okay, you're back from your pause. Where was this graph increasing? Ms. Young, do you want to write it, or shall I? I'll write it.
You can write it.
-5 to infinity. And let me see, it would be decreasing from negative infinity to -5. Okay. What about the last one? This one. Oh no, your face is in the way, Miss Young.
Usually.
Yeah, you're pretty much always in the way, or at least I think you are. This one's constant everywhere. So how do I write the whole number line? Well, it goes to the left and the right forever and ever. So it would be negative infinity to negative infinity, or positive infinity. And I don't really need to write positive infinity, but I started messing up, so I tried to cover myself. Okay? Don't laugh at me. It only makes me do things stupider. Okay? Are we good here?
We're good. Let's move it on.
All right, keep moving on.
Brilliant people watching this, and they're like, dang, that slide took too long. Come on, people, move it along.
Okay. Well, let's see what happens when we move on to a more complicated one. All right, so now we got a graph like, one you may not have seen on everyday life. And there's all kinds of weirdness going on here. You want to do your little highlighting thing. So we're looking for parts where the graph is falling from left to right. And I think you did green for falling.
So I can do green again. What I would do is I would actually pick a highlighting color, and I would highlight to the point that it changes, and then I would change my color, right? And then I'd go back after the fact and decide, is that part increasing or is that part decreasing? So if I look from left to right, my graph is falling. And then right here at this point, something changes. And then I might change my color now and continue along. And then right here at this point, something changes again. Okay, then I would continue on. At this point, something changes again.
But this time it's going up.
Yep. And then one more time, it looks like I've got a pretty consistent pattern, falling pattern from that point forward. And so the highlight on the x-axis is now I'm seeing I'm going to have 4 separate intervals that I need to be talking about along this graph.
So if I were going to take her first one, that would be negative infinity to, what is that? Oh, I put your face right over top of it again. Quit being in the way.
I'm just so good at it.
Put you off the screen. Oh, no, I didn't. You dang you. To negative 1.
Yeah. Notice he's pulling x value, not the y value. So be careful with that. Look at the x-axis.
And I said that's going down, so I'm going to say that one is decreasing. Okay? Now we're going to look at what she highlighted in orange. That is, let's see, negative 1 to, what is it, 3 on the x-axis? What's happening on that one? What happened to the graph then? It's flat, so it's constant.
You know when people talk about a heart rate, and you know when you're looking at a heart rate, it's like tick, 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 and then they have a flat line? That's not good.
Yep. But it's okay on the graph. I mean, it's just what it is on the graph. It's constant. We say it's constant. The next section she highlighted is the graph going up, so this one is increasing. And then finally, from 5, I don't know why I did it that way, to infinity, the graph is, what is it doing again? It's decreasing. Okay, not the worst thing in the world, but we can, this is about as hard as I can make it. Okay, cool.
Let's move on.
Okay.
Move on.
Gosh, nobody wants to hear you sing.
Everybody wants to hear me sing.
All right, this is why we, okay, so we're gonna look at, if you notice, there's places where the graph changes from increasing to decreasing or whatever, and those peaks and valleys in math we call relative maximums or relative minimums. When you're asked to do this, if they ask you to find the relative maximum of a function or the relative minimum of a function, they implying that they want you to find the y value. I ain't gonna do this one by hand, so we're gonna use the calculator here. And I'm gonna, let's see, the best letting plans, I need both of them open, don't I? So I need to get out of presentation. Go ahead.
I'm doing this. He just told you that when you're asked to find the minimum or the maximum, you're asked for the y value. And that's because the x value is where something happens, and the y value is how much that thing is. Okay, so that's kind of why he told you we're going to pull the y value. That's a lot of y's. Is because x is where something happens and y is how much.
Okay, so we're going to orient you to the TI Inspire today, and I think some of you you may have never used this before. So when you turn it on, it should look like this. Okay. And what you're going to do is create a new document. So you can arrow around by pressing the edges of the touchpad. Okay. I'm going to put you over here for a moment. And you can even arrow down through. And we want to make a new document. I could have gotten there by pressing 1. Okay. And now I have a new we'll talk about what we do when we have multiple things going on at the same time in Inspire. But right now we're going to only worry about making a graph. So I could arrow down to graph, or I could have pressed 2. I don't care what you do. So if I choose this, I have a blank graph screen. And this is why I needed to like resize some things, because I can't see the function and my calculator at the same time. So I want to type this equation into my calculator, and your screen is above the buttons, but you know, I'm doing the whole teacher thing here. 0.1, and then where is the X? There's no X button like on the 84. Oh yeah, like see these letters down here that are like an alphabet? They're an alphabet and they work. Okay.
Oh
and what? It's an alphabet.
Yep.
Okay. So this button here is X. All right. That was the joke. Or maybe it wasn't. I don't know.
And
X.
make sure you use X, because notice how that line that he's typing into where it says F1 of X, that's defining which variable we should be using at that point. So,
And the calculator uses function notation. It does F1. It calls, remember I said we could have called it Bob of X if I wanted it in a previous video or something. The calculator calls it F1, but then it has an F2 and an F3. Just like if you've used an 84, it has Y1, Y2, Y3, same kind of deal. Okay? So I'm going to just keep on typing, and Miss Young's probably going to entertain us. Oh, no, she's going to take a drink of, what in the world was that? Oh, my gosh.
so as he's typing in right now, you may have to end up adjusting your window or something like that. This one's so nice because it happens within your window. I would imagine that Mr. Bobby probably chose one that happens in your window.
I would never do that on purpose.
But remember, you can adjust your window by clicking on the numbers at the ends of your axes there.
And we'll do that in the next problem. Okay, we're going to do that in the next problem. So thank you for like jumping the gun. Okay.
Sorry, as usual.
Right. So if you've used an 84, you can find maximum minimum. There's a real convoluted way to do it. It's really super easy on the Nspire. Okay. Everything you need in the Nspire is going to be most.
Wait. Before you do this, because you're going into calculator talk right now.
Yeah.
Remind us what we're looking for.
We're looking for this point right here.
Why?
That's the maximum. That's the highest point on this, the highest point in this little area where it turns from increasing.
Anytime the graph changes from increasing to decreasing and creates a hill, we call that a maximum.
A relative maximum, but yes. And then down here where there's a little valley where it changes from decreasing to increasing is a relative minimum. Yeah. Okay, and that's what we're trying to find. And there's a way to do this in calculus, and there's a way to do this with, but you'll learn that if you take calculus. But right now, we want to use the calculator, and we're just getting oriented in case you haven't used it. So most everything that you'd ever need to find that hill and that valley is going to be one of two places. It's either going to be under menu or this button immediately to the right of the 9. The button to the right of the 9 is all your templates for like doing square roots and stuff. We're going to use that a little bit later on. But if I hit the menu button, all I need to do on this graph is you can see some of these, like I can change my window, that might notice. But I want to use trace, number 5. So if I go down to number 5 and choose trace and then choose graph trace, again, I could hit 5 and then 1. What that's going to do is that's going to put me on the function where I can trace. And notice it said y-intercept. And when I keep going, ooh, it found the maximum for me, okay? So I don't have to do that funky left-right guess thing that you might have to do on an 84. If I smash the enter button right now, it marks my maximum, my relative maximum, at negative 0.082. And then if I scroll over, trace over to this guy, oops, should have, there it was. There is my minimum. And if I press enter, it will mark that point for me. Super, super easy. Yeah. Okay? So hopefully you like that. You can hit escape to get out of that, and now I have my answers marked. Yeah. Okay?
And I don't know, we haven't talked about this, Mr. Bobby, because some teachers expect different things. If you ask for a relative minimum or a relative maximum, will you let students give it as a point, or will you ask them to give it as 2 at x equals negative 0.82? You
better be careful depending on your professor. We probably are cool enough. I would let you go. I wouldn't mark you wrong, but you probably will have that professor who would.
Yeah. Okay. So remember, guys, the maximum, the height of the curve is right here. And it's happening right here. And the minimum is here. And where it's happening is here.
Okay. Hey, was that the answer you were fishing for? Yeah, I figured that's what you wanted. All right, so let's go back to the slides just for a minute because we're going to come back right back to the calculator. Okay, so we use the calculator. I'm not going to write all that down. Miss Young had it there. But there's a problem, and I put this in for a couple reasons. One, because Miss Young always likes to have word problems and everything. You know, she's a stats person. And by the way, I didn't show you my shoes today. Ooh, look pretty.
Ooh, nice. I
Nice.
like that you actually just went ahead and pulled it off the shelf this time. Like, guys, I didn't bother to put my shoes on for you. Um, not that I have shoes on, but just
right now, right now we're wearing shorts. No, that's true. Okay. Anyway, so this problem is about the temperature of a patient, and this is actually a pretty big deal if you're lived through all the COVID stuff. And this is what scientists would love to know about any disease, but basically there's a there's a formula. Maybe this is a disease or an illness that we are very familiar with. And once you get it, you follow this pattern of being sick for 12 days. And your temperature may vary throughout your illness, okay? And we'd like to know when you're going to reach your maximum, because that's when you're the sickest and possibly when you're going to start to recover.
right.
Okay? So we have a function, and I'm going to do the same thing I did a moment ago and type it in. Now, I don't want to, notice I have a page, I have a little tab that says 1.1. What I want to do, that's what we call, on the Inspire, we call that a page, okay? And we're going to make another page. So if you hit, to do that, I want to insert a page. You see plus page right here in blue. To access that, I need to press the button that's blue. Now, I think if depending on the calculator model you have, it might be yellow, and the words will be yellow, but it's the button that says control, and then I hit that dock button that says has plus page above it, and I can insert a new graph. And this is really cool because I have a whole new clean slate of paper. It's like I worked a problem and then got a new sheet of paper and worked another new problem. Okay, that's kind of cool. All right, whatever. So now maybe I'm more impressed by it than you are, but I'm not. I like it. So anyway.
As he's graphing this, because he's about to start typing it in, what you're going to notice here, and then this is what he was talking about, is you've got this rising temperature, and then all of a sudden the temperature is going to start going down again. And so what we're going to be doing is analyzing this rise of body temperature, this fever.
Air graph.
Yeah.
Air graph. Air graph. What? Oh, sorry.
So now we have an issue because he just freaked out, as you saw, because he typed in a perfectly reasonable thing, or what looked like a perfectly reasonable thing, and we got nothing. So let's take a look at what he typed in the calculator, please.
Okay, now look at that equation. That's what I typed in. I didn't mess up. I swear I didn't mess up. Okay? So I typed it in, and it wasn't an entry. There was a y equals or f of x entry line, and it's gone. To get that back, you can hit tab. But I typed it in F2. Now it says F3. Notice that? So to go, I just press the up arrow to go back. And I typed it in right.
Yeah.
I'm not seeing it.
This is important to note right now because he hasn't mentioned this, but if he had typed T instead of X, because technically it said T.
Yes.
If you type T, it's not going to understand T because it's F of X. So you will have to replace T with X like you saw there.
Yeah, I had to translate to the calculator. I'm sorry, I should have mentioned that. I thought you were going to say that earlier. But
shut up. I did say it. So, Mr. Bobby, if we type something in and it looks perfectly reasonable, we fixed our variables, we know our variables match, we know it should be showing us a graph. How should we fix that?
Well, first of all, maybe we ought to look at the context and think about it. What does this measure? And if we're talking about humans, and I see something very familiar, I see 98.6. I don't have a temperature. If I had a temperature of 10 degrees, I would be dead.
You'd be a human popsicle.
I would be a popsicle, in fact. Yes, I'd actually be underground, unfrozen tundra. Okay.
I'm not underground, just.
No, I'm not, and I have.
In a freezer.
So something is wrong with my settings here, and if I press enter, it's because the graph only goes up to 6.67. Okay, the calculator window. So
remember, I told you the y is how much, right? How much?
And this is why we needed to be real clear about the Y value. If I'm trying to find the temperature, I'm talking of the Y values are the temperature. I need this value to be much higher. So I want you to point at it, okay, when your hand goes up there or whatever. Your cursor turns and give it the finger, okay? And when you...
So when I run a fever, I probably would run like 102.
Right.
So maybe we go a little bit more than 102 so we can make sure we get a good curve in there.
Yeah. So what I want to do when I'm pointing at it, I want to open that for editing. How do I open like a file on my computer? I click on it. So that center, that little touchpad where there's a little arrow, if you click the center of the touchpad, it'll open up for editing.
Yay!
And then you said 102?
Well, I think we should go a little more than that, like 105 to give ourselves a little wiggle room.
Okay, we can wiggle. All right. And so we can see now that the temperature is on there. It was just above the graph, okay? Now I could trace here. I'm going to quickly redo that, okay? So instead of, I could have made this 110. It looks like I needed more wiggle room. But if I want, remember the problem said you were sick for 12 days. I want to change this 10 down here. While I have that 110 open, if I hit the tab button, it moves me to the next value and I could change that to 12. And then if I hit tab again, it moves me to the bottom, and I don't really care about negative temperatures. And honestly, I don't care about, temperatures even below, like say 80, right?
And it's weird here, guys, because, you would expect to have, when you're looking at it, you would have expected to have a more defined curve. So what he's doing here also is trying to really see that more defined curve by kind of narrowing in on where we're interested.
And then if you paid attention to the previous one, to find this peak or the relative maximum, I can trace to it. So if I press, again, menu, trace, graph trace, and then I can just arrow over and find out when I'm going to be the sickest.
And I want to point this out here because this is a good moment to do this. As he's scrolling around on trace, and at the bottom right-hand corner, you can see, like on the 6th day, right, my temperature would be 102. And so if you keep scrolling, every point on this curve is going to represent a time, the X value, and then a temperature, the Y value.
And on the 12th day, you're fully recovered. Okay? And I mean, that's in a sense, that's what we were scientists were trying to do with COVID-19. They didn't have the formula. They had to gather data to try to build the model. If this were a model or a disease we were very familiar with, we might know what to expect. Okay?
And if that makes you curious, maybe at some point you should take statistics.
Oh my goodness. Oh, great. All right, back to present mode, or at least for temporary, because we're probably going to come back to the calculator again. The next thing we're going to talk about is something called piecewise defined functions, which I'm not sure you may have ever seen before. But I have a question for you, Ms. Young. Have you ever used or lived by different rules in different situations?
Sure, I have. When I go to work, I have to wear like really formal clothes. And when I am at home, I always wear sweatpants. It's happening right now.
Oh my God. No one wants to see your sweatpants, all right? So yeah, and then, I mean, I was a football player. I acted different and said different things on the football field than I did in my classroom, than I did at my grandma's house, okay? So we all are familiar that you might have different rules for different situations of your life, okay? I don't want to get into the fact that rules may change in your school. I don't want to talk about that. But you know what I'm talking about. It's different. If you're in different environments, you act differently, or at least you're supposed to, okay? And that mathematically happens as well for functions. There's different situations where we might want to apply different formulas. If we get to, when it gets too hot, people have to adjust their exercise routines, right? You can't run as far or as long when it's 105, right, Miss Young?
Or like how much you're going to pay for shipping when you order something on Amazon.
Right. If you have to pay for shipping up to a point, and then afterwards it's free, or you get reduced shipping. Okay.
Right.
Yeah, that's why I always buy $25 worth, at least $25 worth of shoes. No, I'm sorry, $50 worth of shoes from the place that I order them from, because I get free shipping if I order more than $50.
Mm-hmm.
All right, here's an example of what we call a piecewise function mathematically. We have three different rules for three different intervals of x. So when the x values are less than -2, I'm going to follow the rule x minus 1. Okay.
So that right side that he's talking about right there, that would have been the highlighter from the beginning of the lesson where I was highlighting on the x-axis, right? So if you can imagine that, and maybe we'll do that. That x is less than -2 would be a highlighted region. And for that highlighted region, we would be seeing the graph for x plus 1. But we would only see x plus 1 in that highlighted region.
Spoiler alert, this is how I made that graph that was freaky earlier on. When I'm between -2 and 1, including -2 and 1, I'm just constant at 5. And then finally, when I'm for numbers bigger than 1, I'm going to follow the rule. I'm going to square it. Okay? So that's all that means, is there's going to be three different intervals along the x-axis where we're going to be following three different mathematical rules.
So a little memory work here from your previous math classes. That means a piece of our graph will be a line, like y equals mx plus b. A piece of our graph will be a constant function, which is just a horizontal line. And another piece of our graph will be part of a parabola.
What piece of my heart will be?
Stop.
Okay, so moving on. Oh, and clearing the drawings. And then moving on. So how do we evaluate? We evaluated functions earlier. How do we evaluate a piecewise function? Well, we have to look at the number and decide which piece it belongs to. Which piece of my heart does it belong to? Okay, so for the first one, I have to look at -5. Where is -5? Which piece is that? What do you, why, oh, that's ugly color. Okay, well, that would be, so I asked myself, is -5 less than -2? Bingo. So I have to use the first rule. So this would be -5 plus 1. So I'm using the first piece, and she highlighted it for me. Thank you, Miss Young. And that means my answer would be -4.
So you have to do this kind of backwards, because before you can go to the first part of the function, you have to check it with the second part of the function. Like the answer will be this, if this. Well, you have to check the if piece first, okay?
Again, if I look at the next problem, part B, -3 is still less than -2. So I would do -3 plus 1, which of course is -2. All right, super fun. What about 0? Where is 0 less than -2?
Nope.
Nope.
What between -2 and 1, Mr. Bobby.
So I got to use orange.
Yep.
This guy, we like colors, okay? So orange 0 is between -2 and 1. So what's my answer here? What's the rule?
We'll plug it in for x, Mr. Bobby.
I got to plug it in for x, but there ain't no x.
Wait, there's no x?
There ain't no x
So
for this.
what you're saying is the answer's constantly 5 in that -2 to 1?
Well, I don't know what else to do. There ain't no x.
All right, the answer's 5.
Okay, then it's 5. Yeah, if there ain't no x, then that's like super easy. Okay?
Yeah, don't let that confuse you.
Yeah, I think we might have made that worse. All right, what about f of 1? Where does 1 fall? Is 1 bigger than 1?
1 is 1.
1 is 1. Yeah, and it's the loneliest number. But that's, if I put 1 in there, 1 is less than or equal to 1, because 1 is equal to 1. So guess what? This is still 5. And that one's super confusing because that's constant and one of the endpoints. Okay.
Right.
I'm going to highlight the last region so I can decide which one I need to use here because 4 is bigger than 1. What color did you highlight it, Miss Young?
Blue.
Oh, okay, sorry, blue. So this one is bigger than 1. I took a different shade of blue. So I'm going to do 4 squared, which was my favorite game on the playground. And 16. Did you ever play 4 squared?
Yeah.
Okay, this one is bigger than 1, so it's 10 squared, which is 100.
I liked that bar that you could put your knee on and go like.
Okay. You're probably the kid who did the seesaws and jumped off when the other kid was in the air. That
100%,
was.
yeah.
Is it a seesaw or a teeter-totter? What did you call it here in the South?
I called it, well, I was in Boston for half of it and Arkansas for half of it. So
Okay.
I called it both
Yeah.
teeter-totter and seesaw.
Yeah, because that's another regional thing like Coke, Pepsi, or soda.
Right.
Whatever. We're all totally off topic now, but moving to the last slide. So what does this graph look like? Okay, so Miss Young already talked about the highlighting the 3 regions. And Miss Young, if you want to do that, like you could highlight your 3 regions again, and then we could try to figure these out. But then these are really hard to draw.
I would love to figure this out. So I thought we were going to do this on a calculator, but I would
Yeah,
also.
that sounds like this could be like super annoying, right?
My daughter's walking by.
Hi, daughter.
Um,
So I don't really want to do this on the, I'm going to cheat again and show you it on the calculator. Okay.
I'll highlight it on the calculator when you're done. How about that?
Yeah, you can highlight on the calculator. So I'm going to make a new page here on my Nspire. I'm sorry, y'all can still see it, right? All right. So there's my function, and I'm going to make a new page. How did I make a new page again?
I think you hit Control Doc.
That's right, Control Doc. And I'm going to add my 3rd graph of this lesson. And remember I told you there were 2 buttons that were really super important. One was menu. The other was like the math templates to the right of the 9. We're going to use that one immediately to the right of the 9 this time. And if you notice, there's like fractions and square roots and something that like comes from a tree. But what we want, my button actually was on it. I could arrow through that. You didn't even react to something that comes from a tree joke.
I laughed. You just weren't looking at me.
Oh, okay. This one right here is what we want because it kind of looks like what we have over here. Okay. There's a piecewise for 2 pieces, and this looks like a piecewise for 3. But when I choose it, it says how many pieces do you want. I can have, if I really wanted to torture you, I could give you a piecewise function with like 17 pieces. Okay. I don't know that I've ever seen one, but I'm sure they exist. Okay. So I've got 3 boxes that I need to type in. So I'm going to start typing, and Miss Young's going to start talking. Oh, one thing that's really important, you don't need to use the word for here. Please do not type the extra. You just want the inequality. So it would be x is less than -2. Okay.
Yeah. So right now he's typing in x plus 1 for x's that are less than -2, but not using the word for. And what's going to happen is I should expect to see a graph for all the x's that are less than -2, which would start at -2 and go left, right? Or come all the way up to -2. And then the next portion of this, I didn't use the same colors, but it's okay, we'll survive, is between -2 and 1. And so I'm going to expect to see the graph change from -2 to 1. I should see a whole new piece there. And then one more piece here for x's that are greater than 1, I should expect to see x squared, or that parabolic is what it's called, piece for x's that are greater than 1. So let's see what happens.
And I'm going to move the equation out of the way. Now, what's really kind of super cool about this is the one that I had earlier, the pieces connected, the pieces don't have to connect. They can they can jump all over the place. So she said we were expecting a line here. We got a line, and then we got a constant piece. And this is only part of what's called a parabola. We'll talk more about those later. So this is, right.
So something you can't see right now, but you would want to add if you were graphing this by hand, is whether these endpoints are closed or open, right? Because that's going to tell you as the reader if there was an equal to, if that endpoint is included on that graph or it's not included on that graph. So x's that are less than -2 would be this portion of the graph, but not equal to. So technically on the end of this line, there's an open circle and not a closed circle, an open point, like you would see on a number line.
Like,
And if we're looking at, that's right. And if we're looking at that constant piece of 5 between -2 and negative or +1, both of those have equal to pieces, which means we have 2 closed circles on the end points of this graph. And then on this right-hand side, we have only equal to 1, not only greater than 1, not equal to 1. And so we have another open circle on this third piece over here.
okay, I like it. All right, so let's clear all that. Oh, you did it for me already. And come back here. So we're pretty much done. We're done with the lesson. That's the last slide. There are some practice problems for you to look at. I'm sure these are in the syllabus as well, but here you go. And that pretty much completes section 2.1, and hope you have a happy day.
You guys did great.
Bye.
Wonderful.